In this video, I'm going to trace the execution of depth-first search. So depth-first search, it's pretty much the same as breadth-first search. If we look over here on the right-hand side of the screen at the implementation, you'll see that it's got the same neighbor checking loop. It's got the same idea of taking whatever is the next thing off the data structure as the breadth-first search. The only difference is the data structure that we're actually using. So depth-first search uses a stack, and like we saw in the last video, breadth-first search uses a queue. This basically just changes the order of visitation of the vertices. With depth-first search, the idea is that we start at the source node, but then travel as far away from the source as we possibly can, till we hit a dead end. At that point, we sort of backtrack and then try different paths through the graph. So that's obviously different to the breadth-first search, which starts at the source and visits the closest neighbors first before moving outwards to the ones that are further away. But yeah, overall, it's pretty much the same. So why don't we just start tracing through it, and when we get to the differences, I'll just point them out. Differences between this and breadth-first search, that is. Okay, so let's get rid of these. Let's use source 0, vertex 0 as the source again. So let's say we're up here visiting vertex 0. Now for the depth-first search, so we did all this declaration stuff, exactly the same as breadth-first search. One difference in round 0 though, we do not set the source to visited for the depth-first search. You can see over here, all we're doing is pushing 0 onto the stack to get the loop going. So this 0 round for depth-first search, this will look slightly different. We're only going to put 0 there, and then we'll just move straight into this loop. So let's call this round 1 as we go in here. Okay, cool. So first thing you do at the top of each loop is pop the stack. We've only got 0 in there at the moment, so we're going to take 0 out of the stack, and immediately we check if we've been there yet. This is sort of the first difference you'll see in the implementations, just comparing them side by side. See, in breadth-first search, we don't check if we've visited it here. In depth-first search, we do. Now, visited V, so if we're standing on vertex 0, we actually really haven't visited anywhere yet. So this has to be false. We move on to the next line, then we immediately set it to be visited. So in depth first, to me it kind of makes more logical sense. When you actually travel to a node, that's when you're marking it as visited. For the breadth first search, as we saw before, we were setting the nodes to be visited before we actually traveled to them. It's a subtle but important difference between the two traversals. But in any case, we're going to set 0 to be visited now. So we'll go over to the left-hand side of the screen. Let's say index 0 of our visited data structure is now true. And now we print to the screen. So this will be the number 0. So round 1, we're going to print 0. And then we move into our loop. Similar to the breadth-first search one, we're just going to scan across one row of the adjacency matrix. Just be careful when you're answering exam questions, because sometimes they'll do something like this. This loop is actually running backwards. That means we're scanning through the row of the adjacency matrix from the right-hand side to the left-hand side instead of the normal way. So let's look at row 0. And what do we find? We find the number 1 for vertex 7, 6, 5, and 1. So for all of those vertices, we're going to do our 2 basic checks for valid neighbors. We check, is there an edge? The answer is true for 7, 6, 5, and 2, and 1. Have we visited any of those vertices yet? No, we haven't. So for all of them, we're going to set our predecessor and we're going to push them onto the stack. So let's let's write the stack first. So 0 is not in the stack anymore. We've got 7, 6, 5, 2, and 1. So for all of those ones, we need to set a predecessor. Oh, actually, while I'm here, let's put -1. Because 0 is our source, it's not going to have a predecessor. So let's just set all of those to -1. Now we can do these ones. So 7. At the moment, we're standing on vertex 0, looking at all the other nodes. So we're basically going to put 0 as the predecessor for all of them. So for 7, it's going to be 0, 6, 5, 1, and 2. Now, just as a contrast to breadth-first search, we're not filling out the visited array like we were before. So if you remember back to round 1 of the breadth-first search, we'd pretty much filled in almost the whole graph in the first round. Just because in the implementation for BFS, we have the visited being set to true inside the neighbor checking loop. Over here for depth-first search, we don't have that. So our visited is just going to have 1 value there for the one that we're currently visiting. Okay, cool. So that's 1 round of depth-first search. We come back around, check if the stack is empty. It's not, so we're just going to pop the stack. This time we're going to get number 1. First thing we do, we check, have we visited 1? So we look at our visited data structure. Oh, I should put 1 there. Actually, while I'm here, sorry, just give me a second. Let's go 1. So we've already visited vertex 0. So we check, have we visited vertex 1? No, we haven't. That's cool. So we'll set it to being visited now. And once we've done that, we can print it to the screen. Let's get these in here. Cool, so we printed it to the screen, and then we go to our neighbor checking loop again, which will be row 1 of the adjacency matrix. And we find an edge between 1 and 7. So G edges 1, 7, that is true. Have we visited 7 yet? No, we haven't. We check our visited data structure and we see there's still a 0 there. So this is very different. This is where the order of visitation goes different to breadth-first search. Because we had already filled out all of our visited up here, for breadth-first search, we would not put 7 back into the queue. Depth-first search is different. We're only setting visited to true when we actually physically move to the vertex. So we end up with this weird situation where, which you don't see in breadth-first search. We're going to put 7 back into the stack. The predecessor, it was 0 in the previous round, but now we're sitting on vertex 1 and we're putting 7 back into the stack. So at the same time, we need to update the predecessor. This line of code shows that over here. I've got highlighted on the right. So that's very different to what we saw in breadth-first search. Okay. So yeah, we're going backwards through this row. We found an edge to 7, and we've also got an edge from 1 to 0, but checking the visited data structure, we have visited 0. So we don't put it back into the stack. So we were on 0, we came down to 1. Now we've looked at all the neighbors of 1 and updated our data structures. So that's another round of depth-first search done. On the next round, we pop the stack. We can see 7 is at the end. So we're going to print 7 to the screen. Okay, let's grab these predecessors. now we've moved over to vertex 7, we can set it to being visited. Let's do it to all rows to make it easier. Okay. Right. So 7 is gone out of the stack. We set 7 to be visited, and we also need to do our neighbor checking for vertex 7. So let's go to the 7 row of the adjacency matrix, and we scan across it, and we see there's edges from 7 to 6. Have we visited 6 yet? No, we haven't. So we can put that into the stack. And as we're doing that, we should update the predecessor as well. So what are we standing on? Vertex 7. So for 6, we should have 7 there. We've also got an edge to 4. Have we visited 4 yet? 0, 1, 2, 3, 4. No, we haven't. So we can put 4 into the stack. And at the same time, we can set a predecessor. 0, 1, 2, 3, 4. It's that one. So that will be 7. And there's also an edge from 7 to 1, but we've already visited 1. So we check our visited data structure. We see we've already been there. So we don't put that into the stack again. And we find an edge between 7 and 0, and it's the same deal. We've already been to vertex 0, so we're not going to do it again. Cool, so that's round 3 of depth first search. So we go into the next round, we pop the stack. This time we've got the number 4. I'll just copy paste all that. Okay. So we've now moved on to vertex 4. So we should set vertex 4 to be visited. 0, 1, 2, 3, 4. It's that one. And print it to the screen. Okay, already did that. Right, so now we just need to check the neighbors for vertex 4. We go to row 4 of the adjacency matrix, and we see 4 has edges with 7, 6, 5, and 3. Now we've already visited 7, so we ignore that. Have we visited 6? 0, 1, 2, 3, 4, 5, 6. No, we haven't. So we add that to the stack. I should take that 4 out. So we'll put 6 in the stack. And while we're here, we'll update the predecessor. 0, 1, 2, 3, 4, 5, 6. So the predecessor for 6 is now 4. So where are we? Okay, so that was 7, 6. Node vertex number 5. We also haven't been there. So we can put 5 into the stack. And we'll set its predecessor. 1, 2, 3, 4, 5. So it was 0 before. Now we're going to make it into 4. And then finally there's an edge between 4 and 3. And 0, 1, 2, 3. We haven't been to vertex 3. So we can put that into our stack and update the predecessor. 0, 1, 2, 3. Predecessor of 4. Okay, I think that is vertex 4 completely explored. So we move on to the next round of depth first search. If we pop this stack, we're going to get the number 3. So let's just put 3 to the screen. Get 3 out of the stack. Mark 3 as being visited. Just line these up. Okay, 0, 1, 2, 3. So we're now visiting vertex 3. And then we go ahead and scan the number 3 row of the adjacency matrix. 3 has edges with 5 and 4. 4 we've already visited, so we can ignore it. But 5 we have still not visited yet. 0, 1, 2, 3, 4, 5. Still 0. So we can put 5 into the stack, update the predecessor. 2, 3, 4, 5. So that will be 3 now. And okay, what are we on? Vertex 3. Okay, cool. So we printed 3 to the screen, we visited 3, we looked through 3's neighbors and added 5 to the stack. That's another round of depth first search done. Move to the next round and pop the stack. Let's grab all this. Okay, so we got 5 out of the stack. We check if 5 has been visited. It hasn't. So now we set it to being visited. 0, 1, 2, 3, 4, 5. And then we scan the 5th row of the adjacency matrix. And we find that 5 has edges to vertex 4, 3, and 0. Now all of those vertices have already been visited. So our depth first search has run into a dead end. At this point, it's good to stop and just think about like the pattern of visitation. You can see that depth first search is actually moving as far away as it can from the source until it hits a dead end. 0, 1, 2, pardon me, 0, 1, 7, 4, 3, 5. It's got nowhere else to go now. That's the pattern of depth first search. At this point, it's probably going to jump over here to number 6. Because the idea with depth first search is once it hits a dead end, if you think about it, like we're implementing it with a stack, but a lot of the time, well, usually you'd probably use recursion to implement this. At this point, you'd start unwinding the recursion backwards, so like a backtrack. So you hit the dead end, go back to 3, go back to 4, and then you would look for an alternative route. You might go straight to 6, or you might go to 7 and then to 6. We'll see in a second what happens when I start doing it over here. But that's the basic idea. You go as far away as you can from the source till you hit a dead end, and then you start going backwards, looking for paths that you missed before. Okay, cool. So what happened? We visited 5, and we did all that stuff. Now, in depth first search, you can get duplicates in your stack. So there's another 5 there. So basically what will happen is, if we look over on the right-hand side of the screen, we'll check if the stack is empty. It's not. We'll pop off the 5 here again, but then we'll hit this if statement. At this point, we've already been to 5. So this will be true, and we'll do continue. Continue skips all of this stuff. It just makes you go around to the next loop. So I'm not going to do an extra line for that one. I'm just going to get rid of... Oh, no. Okay. Okay. Just going to get rid of the 5, not the full thing. That would have sucked. Right. So actually the next valid thing that we're going to pop off the stack is 6. So let's just put a 6 over here. And let's copy paste this stuff. All right, I'll get rid of that 6 because that's the one we're doing now. Right, so we're visiting 6. Let's set 6 to be visited. That's this one here. Oh, and I forgot to do these ones before. Let's just put 1s in here. Okay, I think that's good. Let's get this. hang on a sec. Right. So we're now visiting vertex number 6. Let's put a star up here. And we printed 6 to the screen. Got that down here. We set 6 to be visited. So all that's left is to do the neighbor check. So we go to the 6th row of the adjacency matrix, and we find that 6 has edges to vertex 7, 4, and 0. Now all of those vertices have already been visited, so we don't add anything new to the stack. So we move on to the next round of depth first search. And just like what happened with the number 5 vertex, we had a duplicate of 6. So I'm just going to delete that one because it would have been caught here over on the right hand side, that if statement. So I've got a number 1 there. Oh, okay. Sorry, I think I've just noticed. It's very hard to talk and think and write at the same time. I think I should have pulled this one out. So if you guys watching, pretty sure you guys probably would have all noticed that. Sorry about that. Okay, so I had 1 in the stack there, and then I went to 1, but I forgot to pull it out. Okay, cool. Right, so what should have been there, at least, yeah, I think that's correct. 2 is the only one we haven't visited yet. So this looks okay. So we move on to the next round. Obviously 2 is on the top of the stack, so we're going to pop that off. We can print it out to the screen. We'll get rid of the 2. Now we can finally mark our 2 as being visited. And now we do our neighbor check. 2 only has an edge to vertex 0. Obviously we've been to 0 before, so we don't do anything with the stack. So it pretty much looks like we've finished, but you'll notice that the stack still has items in it. The implementation for depth first search is going to continue looping until your stack is completely empty. We didn't have this problem when we were doing breadth first search. In breadth first search, we don't have duplicates of vertices in our queue, but because depth first search does allow duplicates, sometimes you get into this situation where you've finished, you've visited everything, but there's still stuff to do. So what will happen is this loop will just run 3 more times, and each time you'll just pop whatever is off, whatever's on the top. You'll hit this if statement and continue. So effectively what will happen is these will just get popped off and nothing will happen. Obviously we've already visited all those vertices before. So that's depth first search finished. And yeah, like I said before, the main point, or the main difference with depth first search is that we're actually going to move as far away as we can from the source before we backtrack and then try different paths. 2 was the last node that we visited in this depth first search, but it's only 1 edge away from the source, and that sort of proves the point. In a breadth first search, that was like the 3rd thing that we visited. So you can see, depending on what the question is that they're asking you, one or the other of these visitation patterns will be more appropriate. The classic for breadth first search is when they're looking for shortest paths, or like some form of distance, something that's closer or costs less to move to. You want it to be as close as you can to the source, so you search those first. Depth first search is good in pretty much all other situations. Searching grids or mazes like you did in the lab, even traversing trees. A depth first search is usually a better way to implement it. But yeah, it ultimately comes down to the question they ask you. When you get a question, just sit down and think a little bit about it and just decide whether this is something like you're trying to find something close to the source or not. that will tell you, do I need a breadth first or do I need a depth first search? And also at the end of the day, even if you're not really sure what the question needs, both of these traversals visit all of the nodes of the graph. So if it's a question that really the only requirement is that you visit all the vertices of the graph, you really can use either of these two algorithms. It doesn't matter. Okay, cool. So that's breadth first search and depth first search.